Okay, YouTube, this is my third video on solving trig equations, and in this video we're really going to look at a particular instance in which, solving the trig equation is made a little bit more difficult by the fact that, well, first of all, I have more than one type of trig equation. So what we're going to do is we're going to try to make this all one type of trig equation. And second of all, you notice that I have a squared trig function as well as a trig function to the first. So when solving, equations in general, when you have, items to different powers, one of our methods of solving is, of course, trying to factor this thing. And so trying to factor this, we already got this set equal to 0. We could try to factor it, but I notice that these share no common factors. Now, if these were all in terms of, say, all sine or all cosine, then we could effectively factor this and then just set each individual factor equal to 0 and solve it. So the first thing we're going to do here is, noticing that I have a sine squared, what if we were to try to pull a trig substitution? That is, we are already aware from our fundamental trig identities that sine squared plus cosine squared of an angle should always come out to equal 1. So what this means is, then we could say effectively that sine squared would be the same thing as 1 minus cosine squared. And the reason why this is such an effective substitution that we're about to pull is that when we plug this in for our sine squared, now everything will be in terms of cosine. So we've got it set equal to 0. Let's go ahead and make this substitution. We say plus 3 cosine x equals 0. And now we'll have this. We have 1 minus cosine squared of our angle. So now, like any, algebraic equation, when you get set equal to 0 and you want to solve it, and you have things in different powers, let's go ahead and clean this up and then try to factor it and set each individual factor equal to 0. So we get 2 minus 2 cosine squared of x plus 3 cosine x. And so I want to clean this up a little bit. We'll put the squared item in front. So we have negative 2 cosine squared. Oh, that doesn't look very good. Cosine squared of x plus 3 cosine of x plus 2 equals 0. And because when I factor, I like to have a leading coefficient that's positive, let's go ahead and take everything times a negative 1. Or you could say we're dividing everything by a negative 1. It's really not going to affect what we have on the right because we've already set this equal to 0. So we have 2 cosine squared x that's positive, a negative 3 cosine x, and a negative 2 equal to 0. Okay, so now that we have this set equal to 0 and it's in a quadratic form here, we're going to try to factor this. And just, if it weren't factorable, we could use the quadratic formula as a matter of fact. But the point I'm trying to acknowledge here is this. We have something that we can definitely solve. So trying to factor this, and I'll tell you, I'll be honest with you, I gave us something that is factorable. We're going to go ahead and factor it. So I noticed that starting with my 2 cosine squared of x, this a value is not 1. So we're going to have to do a little guess and check here. But I think beyond a doubt, we would have to have a 2 cosine x there and a cosine x there. Multiplying the first two here in our FOIL, we would say that this term in our trinomial here, quadratic trinomial, has been satisfied. So now the back, we say negative 2, give me two factors of negative 2. And so maybe I write a, like a plus 1 minus 2. I don't know. That would multiply out to be a negative 2 in the back. The idea is that we're just needing to check to see, do we get this middle term? So in terms of FOIL, the F gave us this and the L gives us this. We have to check our O and our I to get this middle term. So I always like to do this guess and check. We say 2 cosine times negative 2 would be a negative 4 cosines. And then 1 times cosine would be a positive 1 cosine. And if we were to do this FOIL and then combine these like terms here, you would notice that we get a negative 3 cosine of x, which is essentially what we wanted to get in the first place. So having our factors now, the idea is the same thing you do in an algebraic, method of solving here. We're going to set each of these factors individually equal to 0 and solve them on their own. So let's go ahead and kind of block this off here and give ourselves some room. If I set 2 cosine of x plus 1 equal to 0, the first thing we would want to do is we would want to isolate the trig function value here. And then we say, okay, over here we say, well, cosine x minus 2 equals 0. We'd like to do the same thing. So over here on the left, I would subtract 1 from both sides, and effectively we would get 2 cosine x equals negative 1, and then we'll divide both sides by a 2. And so we get, and this is very important here, we get cosine x comes out to be a negative 1/2, negative 1/2. And then over here, I'm going to isolate this trig function by adding 2 to this side here. So we get cosine of x equals a positive 2. Once we have the trig functions isolated, just like we've done in the past, what we'll do is we'll just undo the trig function. We need to use an inverse trig function value to undo the parent trig function. So we say cosine inverse of both sides. And sorry about that. We got to kind of squeeze this in here on the left side of this. You never write it on the right side. But we say, okay, well, this cancels out. And so this is very important here that you write this. But we say x equals the cosine inverse of negative 1/2. That is, this is already telling your audience that your angles, whatever they are, they are the angles that you get, since you took the cosine of something, you got negative a half for an answer. And then over here we would say, well, these cancel out. And I say, well, then x equals cosine inverse of 2. So we'll go ahead and start with this one on the left. The first thing we want to kind of figure out is this. Well, what could I take the cosine of and get a half? Forget the negative just for a minute here. What reference angle would give us a cosine value of a half? What's our x prime or our reference angle? And so this would have to be a 60-degree reference angle. And all I'm doing is I'm just kind of referring to our unit circle. At least the first quadrant, we have pi 6, pi 4ths, and pi 3rds. And sorry about drawing this very quickly here, but I just don't want to take up all of your time. These values are all over 2. We have a unit circle of radius 1, and these are all over 2. And what I want to know is, where's our cosine value equal to half at? So we have 1, root 2, root 3. Going back up, 1, root 2, root 3. But the idea here is this. It's this angle right here that gives us a cosine value just of a half, the number a half. So we would say that whatever this is, it is a pi 3rds reference angle. So using this reference angle, which is really the key here, we are going to go sketch out where would the actual angles in standard position then lie. Knowing the fact that we have this mnemonic here, all students take calculus, we're saying, well, cosine came out to be negative a half. Not just a half, but negative a half. So we say, where could this angle not be? Well, it couldn't be in the second, nor could it be in the third quadrant, because cosine, they have to be in the second and the third. Couldn't be in the first or the fourth because cosine would be positive there. We want cosine to be negative. And we say that we had a pi 3rds reference angle. So what we're going to do is we're just going to go sketch a couple of pi 3rds reference angles here. That is, here's pi 3rds and here's pi 3rds. But the real question we're trying to ask is, well, then what are the angles in standard position between 0 and 2 pi that gave us this? So knowing that this would be, 3 pi 3rds over here, and this is 6 pi 3rds over here at 2 pi, we could say, well, then we're a pi 3rd short of 3 pi 3rds, so this angle here, this first one, had to be 2 pi 3rds, 2 pi 3rds. And then the second angle down here in the fourth quadrant, well, it's 3 pi 3rds plus this other pi 3rd right here, so this is a 4 pi 3rds angle in standard position. So these are the angles that we're after. These are effectively what we call the solutions. And then the only thing we need to acknowledge is this. We need to add on multiples of the period of cosine. And the period of cosine is 2 pi. Because if we were to rotate one full rotation on top of this, say, 2 pi 3rds, we'd be back here, and we'd be landing in the same spot and still getting a cosine value of negative a half. So these are a couple of our solutions. My favorite solutions are from this one right here because they do not exist. The idea is, I'm asking what reference angle, let alone angle, but what reference angle would give you a cosine value of 2? Well, what we know about at least the unit circle and helping us remember this is that the radius is 1. Like this is the 0.01 and this is the 0.10. So we would say, where on the unit circle would I ever get a cosine value of 2? We say, well, you're never going to have an x value of 2. There's no angle that you can rotate to that's going to give you an x value of 2, or an angle of 2, or a cosine value of 2. So we'd say that these angles do not exist. So the last thing I want to do is I kind of want to just go acknowledge these, looking at this unit circle, but we see that the two angles we got over here, 2 pi 3rds and 4 pi 3rds, if we rotate at 2 pi 3rds, we see that we did get a cosine value of negative a half. And if you rotate down to the third quadrant here, we still have an x value of a half because it has the same reference angle. It's just that we're in the third quadrant. It's at 4 pi 3rds. And last but not least, what I did was I went and I plugged this into Desmos. I graphed it. We say 2 sine squared x plus 3 cosine x. And so we say, looking at this graph, it's kind of an interesting looking graph. But we say, at least where between 0 and 2 pi is this graph at a height of 0? Because recall, we were saying, I want to know where would this thing, this function of x, have a y value of 0. We plug in 0 for y. And looking at this, we say, okay, well, it's at a height of 0 here, and a height of 0 here. And we can easily verify that it was 2 pi 3rds indeed, and 4 pi 3rds. And we could see that just adding on any period of, say, 2 pi 3rds, add on a period of 2 pi, we get 8 pi 3rds, or take off a period of 2 pi, we'd be back over here, and we say negative 4 pi 3rds. The idea is that it's just going to repeat itself indefinitely. Cheers.